Okay, in this problem we have a solar concentrator, and it's sort of loosely described. It says you have a heliostat. It's called a heliostat. It's a solar power tower. 100 mirrors reflected this much power onto a receiving plate. And it talks about the nature of the receiving plate, which is black. It's got a emissivity of 0.9. It's made of this. This is the conductivity constant, and it's this thick. Okay, so it tells you that the sun heats the outside surface of the plate to this temperature, and heat is conducted into the fluid. So honestly, I had to look this up because I didn't really know how these things worked. But so there's some sort of tower like this. This is sort of quite many stories high, and this tower is surrounded by a series of mirrors that aim. I'm just drawing these lines to indicate rows of mirrors. They aim the light at some sort of collector plate here. So this description of the 500 degrees C collector plate that's made of steel is something here, and then on the back side there is some sort of way to get fluid up in here and transfer the heat into that fluid. So the question is, what's the power that's radiated back into the space from the outside surface of the tower? So this sort of relies on you knowing that if you were to define the tower as a system, so let's say we're analyzing this, we know that the energy in equals the energy out. And then if you were to take the derivative of that with respect to time, that would just be, d dt. That would be the same thing as the power in equals the power out, since the power is the change in energy with respect to time. So you've got essentially 400 kilowatts coming in here and into this plate. And Pete's saying, there's negligible convective transfer of heat away from the surface of air. So he said it's a bad assumption, but let's go with it. So here's the energy in. Where's the energy out? Well, first of all, we know that some of this energy is radiated back, reflected out here, and some of it is actually transferred into the fluid inside here. So there's some that is absorbed. Wow, I'm picking a bad color here. Let me use A. So we know in terms of the power in, we know that is 400 kilowatts. What is the power out? Some is, we're going to say, power reflected back into space, plus the power radiated. So we know that this thing glowing at 500 degrees C, well, now I'm not sure if it's glowing, 500 degrees C will actually be radiating infrared light emitting infrared light back into space, or infrared radiation. So that's part of the power radiated, plus the power, we'll just say conducted away by whatever fluid is flowing back here on the other side of this 5 millimeter plate. So that's a setup of the problem. So the question is, what is the power that's radiated back into space? So he's asking for this term right here. Now let's go over to the equation sheet and just remind ourselves the different terms that we have. So let's see, do we have any equations here? This is the area where you've got the equations for heat transfer. You can see here the change in heat. This is for, let's see, heat capacity, number of moles, C times delta T. Here we go, heat conduction right here. So dq dt, the change in heat energy with time, that should be dt, that should be a time. I would make that a small t, not a big T. Big T is temperature. Minus kappa times the area. This is the thermal conductivity coefficient times the area times change in temperature with respect to x. So this is linear heat transfer through one-dimensional heat transfer through some distance x, dx. Or it equals area times the emissivity times the Stefan-Boltzmann constant times temperature to the fourth. This is radiative heat transfer. This is conductive heat transfer. Let's sort of bring that equation over to our space that we're working on. Let me make this. Gotta find my mouse. Okay, here we go. There's not room for me to work here. I'm just going to draw this down here. I'm going to say that our change in heat with respect to time, so this is also known as power. This power is equal to negative K, or kappa, times the area, times the change in, basically the temperature gradient, dt dx. This right here is the power that is conducted away. So this is the heat that is transferred through the plate. This is a terrible drawing. Through the plate, this 5 millimeter plate, into the fluid that's back here. We also know that the power is equal. These are not the same things. That's for power for conductive away. We also know that the heat transfer with respect to time can be found by looking at the radiated power, the area of radiation, times the emissivity, times the Stefan-Boltzmann constant, times the absolute temperature to the fourth power. This is the power that's radiated back into space. That's this sort of drawing right here, by this 500 degrees C steel plate that is radiating power back into space. That's this one. Now, there's a reflected power. What's that? Well, this is not a perfect absorber. We know that some sort of, I don't know what it is, Kerkoff law or something, Kerkoff's law of heat. I forget what it's called. But anyway, basically the absorbance, I'll use an A, I'll use an A, it's supposed to be an A, is equal to the what's emitted. What's absorbed is equal to what's emitted. So here we've got the emissivity is equal to 0.9, which is essentially the ratio of what's absorbed or what's emitted to the incoming. I guess the total. I'll just put TOT. That's supposed to be total, not transmitted. So 90% of that is actually absorbed and re-emitted. 10% is reflected off. Okay, so there's a lot to know in this problem. So we're looking for the power that's radiated back into space. So which term we're looking for? We're looking for this one right here. We know it's radiated through black body radiation. So let's go ahead and compute this. Okay, so here's my equation: A times emissivity sigma, but Stefan-Boltzmann constant, T to the fourth. All right, now that is the power that's radiated out. So the area we know is 2 meters squared. That's given in the problem. The emissivity is 0.9. The Stefan-Boltzmann constant is here. I'm going to call that 6 times 10 to the minus 8th. Now, Pete's just going to have to deal with it. Watts per meter squared, since I don't have a calculator. Kelvin times T to the fourth power. Holy Moses. Okay, so T to the fourth is that should be Kelvin to the fourth. There we go. Kelvin to the fourth. So T to the fourth here. We know this is 500 degrees C plus 273 makes this whole thing Kelvin. 500 plus 273 is Kelvin. So this term right here, I'm going to call this, it's really 773 Kelvin. I'm going to call it 800 Kelvin. And this is raised to the fourth power. 800 Kelvin to the fourth. Okay, so now I'm going to reduce this whole thing. So we've got dq dt. The rate of power radiated is equal to 2 times 0.9 is that's 1.8. I'm going to call that 2. Well, all right, I'll write down 1.8 meters squared, and maybe I need a different color here. Meters squared, this cancels. Kelvin to the fourth out here, that cancels. So we've got 1.8 times 6 times 10 to the minus 8th times 800 to the 4th power. 8, I'm going to write that 8 times 10 squared to the 4th power. The kelvins has canceled, so now I have watts. Okay, so what I have is 1.8 times 6 times 8 to the 4th power, and notice 10 to the squared to the 4th is 10 to the 8th times 10 to the 8th. That just cancels. So this many watts. Now 1.8 times 6 times 8 to the 4th. 8 to the 4th is, I guess, 6 times 64 times 64 times, I'm going to just call this 2, and whatever. This is what you have here. The math actually sometimes slows me down because I'm not so great at multiplying this out very quickly. So we've got 12 times 64 times 64. I'm going to call that 64 squared. I'm going to call that 3,600. I know that's not right. 2 times 6 is 12 times 3,600. 12 times 36 is 36000. It's 10 times 36 plus 7,200. 00. Carry 1 4. This is about 43 kilowatts is what is radiated back into space.